Right, so in this particular lecture, most of the time I think we will be talking about the pulse latch. So pulse latch is another kind of a latch or another kind of a sequential elements where where the level of the pulse is not as high as that of the clock signals. And in some of the digital circuit designing or the VLSI design, we will require this pulse latch to be incorporated for getting the right output. Right, so moving ahead, so what I'll do is in this particular slide, I'm just going to talk about the clocks that has been used for all the three sequential elements. Right, so let's get started with the flops design. So for the flop design, we apply a clock here, and then generally the clock is of particular frequency, and for the 65 nanometer technology, we will generally use a clock of frequency 1 gigahertz. So I'm assuming we'll be getting around 500 picoseconds here, and 500 picoseconds for the clock level low. So the flip-flop will be working only during this particular portion of the clock. So only when it sees for a positive edge triggered flip-flop, only when the clock does the transition from 0 to 1, we will get the output. Right, now whereas for a latch, the latch is always defined with respect to the level of the clock. So in that sense, the latch will be designed with respect to so if I draw the another clock here of the similar frequency, and yeah, so this is my 500 picoseconds and this is my 500 picoseconds. And the latch here is likely to work only in the positive level of the clock, right? So the latch will throw the output only during the whenever the clock is at a level high for a high level of the latch design, right? Whereas for the flip-flops, it is always with respect to the transition. It's of the clock, whereas in this particular case, it is the positive edge triggered clock. So in the positive level of transition, you will get the output. Right. So in the subsequent clock transitions, that is where we will get the output in the flops. Whereas in the subsequent clock level high, we will get the latch output. Right. Now the third one is a pulse latch. Now the pulse latch, what it really, where it will be really useful is, if you want a design or if you want the combinatorial circuit output to be captured really at the edge of the clock, right? But we may not have that kind of an allowance, or rather we may not have that kind of a tight constraints that it will, it will be timed properly at the edge of the clock. But at the same time, I don't want to use the level of the clock because it is high for almost, majority portion of the clock signal. So in the sense 500 picoseconds and 500 picoseconds for the clock level high. So we don't have that kind of a luxury or the allowance also. And in that sense, what we do is design a clock or a pulse signal, right, for a shorter duration. And then it will be level low. So what it really means is I don't have that kind of an allowance here as that of the clock that has been provided to the latch. So I don't have that much of a room here, the high level. But at the same time, we don't have that much of a tighter constraints where the output should be captured at the level. So there is some kind of a room here in the pulse signal. So that's why this particular pulse signal will be acting as a clock for the pulse latch, right? So if I pass this particular pulse to any kind of a latch signal, then it will it will be called as the pulse latch. So the pulse latch is if I design the latch part of it, it is very much similar to the latch any regular latch. Only the clock signal that is being provided to the latch design, if it is a pulse signal, then it becomes a pulse latch, right? And just to complete this particular portion, we'll say that this is also clock, but it will be useful for the latch design. And this is also clock, which will be useful for the flip-flop designs. And this is a pulse, which will be useful for the pulse latch operation. right? Hope this is clear. And just to just to give a little bit additional information is the pulse level here. Note that this is not of the same duration as that of the 500 picoseconds here. Now, it turns out to be that the duty cycle of this, the duty cycle will be nothing but the pulse level high divided by the pulse level high and then the low. So it is generally around 18 to 20% the duty cycle. So roughly around if it is 100 or rather 1000 picoseconds, so this particular time duration will be a maximum of 200 picoseconds. It will be less than that. Hope this is clear. So this signal we want to apply it into the latch and then get the pulse latch output. The other additional information here is, whereas when I compare the pulse latch as well as the regular latch, the operations, the combinatorial circuits output will be captured in the positive level of the latch, and then the another combinatorial circuits will be captured in the negative level of the clock, and then so on. Right, so because we have so much of room here in the latch design, so much of room in the clock that has been provided to the latch design, we want to utilize the entire portion of this particular clock level high, and don't wait for the clock level getting high in the next cycle. So we also use the clock level low here. Right, so most of the latches are actually used in pairs of and forms the phased transparent latch design. So the combinatorial circuit number 1 will operate here, and then the combinatorial circuit number 2 will operate here, combinatorial circuit number 3 will operate here, 4 will operate here, and so on. Right, so that the combinatorial circuit output, whatever is the output will be getting captured in the in this low level here, and that output will be provided to the combinatorial circuit number 2, and that output will be captured in the in this particular level, and then so on. Whereas in the pulse latch, this particular latch is because it closely follows the flop designs. Also, we don't have that kind of a tighter constraints. But at the same time, whatever is the the combinatorial circuit data path which we choose, right, the similar thing will remain here for the pulse latch. So if I'm designing combinatorial circuit here, it should be captured in this. The output should be captured in this particular pulses, in the pulse number 1, right, and then it will go to the subsequent combinatorial circuit, and that should be captured in the second pulse. So we don't utilize this low level of the pulse signal, very similar to that of not utilizing this entire portion of the clock that is being supplied to the flip-flop designs, right? So only in the latches, because of this a majority of the room that is been available, right, we tend to use and capture the signal in the low level, as well as apply the phase latch which will be able to capture this low level also. Right, so here the latches, we always use it in pairs, whereas in the pulse latch it is always a single pulse latch, and it will be operating at every different pulses, similar to that of the flip-flop designs, where the flip-flops is able to capture at every rising edge of the clock in this particular design. Right, hope this is clear to everyone. Moving ahead, now how do we generate the pulse signal? Right, one simple design is actually to use a clock and then feed it to an AND gate, and the other input is nothing but the inverter. Right, so what really happens is, if I have an AND gate here, and if this is the signal that is being provided to the AND gate, and the inverted output of the input, so this is the clock signal which is given to the input. The inverted of this clock signal will be nothing but high and then low, and then high and then low. Right, so because of this delay in the inverter, we are likely to get an output here which will be nothing but high for this particular duration, and then low throughout. Right, so that is what we are trying to use this concept. So based on this inverter's delay, we are likely to get this pulse duration, right, or the pulse width. Right, just in terms of the CMOS technology, we cannot use an AND gate, so we are using a NAND gate and then followed by the inverter here. So we have a clock signal given, and then the pulse signal is being generated from the clock signal. So remember that in a chip design, we always have very few number of clocks source circuit or the clock generating circuit giving a clock signal of 5, and from that we will be using the pulse signals, or we'll be generating the pulse signals. So in this case, the clock is provided to the NAND gate, and then the inverted of the clock is is given to the another input to the NAND gate. The output of that is going to the inverter. Right. So if I look into the timing diagram here, very clearly it says the clock signal, and then the clock bar signal, which is provided as a second input to the NAND gate, and there will be a delay, and that particular delay is due to this one particular inverter number 1, right? That is this inverter. And then because of this, this being high and then this being high, the output of the NAND gate will be low here. Otherwise, for all other cases, the output of the NAND gate will be high, right? So there will be, this will go to low due to, for with respect to the rising edge of this clock signal. So TPD of the and then this will go high whenever the phi bar goes low. So we will have this propagation delay with respect to the phi bar signal, and this one is going low with respect to the propagation delay of the clock signal, right? So this particular duration is what is generating the clock signal. The output of the inverter here will be nothing but the inverted signal of this phi bar P signal. So we'll get the pulse signal here, and then the delay due to this is due to the delay of the generating the pulse signal from the pulse bar signal will be nothing but the delay of this particular inverter, which is stated as TPD inverter of 2. All right, and this particular delay, we call it as the output of the NAND gate with respect to this clock signal. We say that it is the TPD of the 2-input NAND gate from the clock signal, and then this one is the TPD of the 2-input NAND gate coming from the clock bar signal, right? So the pulse width here is actually determined by this particular overlapping ones, right, in phi and phi bar. And that is arriving due to this particular, the inverter, which is generating this phi bar signal. So the first inverter here, right? So the pulse width is characterized by the inverter's width or the inverter 1 dimensions, right? And this could easily be also be the 3 inverters. So if I have a 3 inverters, it is likely to be of the same dimensions, which is there for the 1 inverter. Then odd number of inverters is likely to give me a little bit more delay, so little bit more overlapping ones here among the phi and phi bar, and thereby I will get a larger pulse width, right? So for generating the pulse signal with a pulse width, this simple circuit can be utilized comfortably, right? Moving ahead, so generally we will have a pulse generator signal with an enable signal. So without an enable signal is what we had seen now. The phi goes to the NAND gate. The other input of the NAND gate is an inverted of the clock, and then finally it goes to the inverter. So if I draw the schematic of this, it will be the NAND gate, 2 of the PMOS transistors in parallel and 2 of the NMOS transistors in series, and then you have the phi signal going to the PMOS and NMOS, and phi bar signal which is going to the PMOS and then NMOS. And then the output of this is going to give, it will be provided to an inverter to generate the pulse signal here. The pulse width is always determined or characterized by this inverter's design, right? So whatever is the inverter's delay is likely to give me the pulse width value. Now with an enable signal, if I want to add the enable signal, ensuring that only when the enable is high, that is when I'll get the pulse signal here, pulse signal going high. Otherwise, the pulse signal will be low throughout, right? So for that particular case, an enable signal is provided to 1 additional transistors here in the pull down circuit of the 2-input NAND gate, right? So this particular part of the circuit is very, very similar to this particular part of the circuit. The only thing is the enable foot transistor or the enable additional transistor is added in the pull down circuit of the 2-input NAND gate, right? In the pull down circuit here we have 2 transistors. Here it is actually 3 transistors, where one of the transistors is enable. So if the enable is not 1, then the pull down circuit will not work. Only when the enable is 1, we will have the pull down circuit. So this 5p, the complement of pulse signal or the output will be able to discharge to the ground, right? Unless that happens, unless the enable is 1, if the enable is not 1, then the 5p bar signal will always be considered to be in the previous state or to be high, right? Only when it is 1, this will go down, assuming that phi and the phi and phi bar are both 1, then it will go down and then the 5p will be generated, right? Hope that is clear. Just to reiterate that in a timing analysis, so we have the clock signal here and then the inverted clock, which is, we have the overlapping ones here because of the first inverter delay. And if let's say the enable signal is made only high, only in this particular instance, right? All other instant it is low, and then from this instance it is high. So even if there is an overlap here, right, we will not get the 5p going down. The 5p should go down, right? That doesn't happen because this particular transistor is off because the enable is 0. So here it will stay to 1, the 5p signal, and or 5p bar signal, and 5p the pulse signal will be 0 here, right? The moment the enable becomes 1 here, this overlapping ones here be generated due to the inverter number 1 here, right? So this particular overlapping ones will generate a low 5p bar signal. So it now, because the enable is high, so this particular transistor is on, this is also on, this is also on, so I'm going to write it on, and then this is also on. So the 5p bar signal will go down. That is what is happening here. And then once it goes back to low, then it will go back to high, right? So we will get this 5p bar signal, and then the pulse signal will be generated with a pulse width here, which is of course determined by the first inverter, right? So that, this is a very simple circuit providing the pulse signals only when the enable signal is high. So an enable control signal is also being accommodated in this particular circuit. So the pulse width of is nothing but of 1 inverter delay. In this particular case, this is the inverter delay we are talking about. Generally, it is 1/6 of the cycle. The pulse width is 1/6 of the cycle. So if it is so the time period or the pulse width will be 1/6 multiplied by multiplied by 1 by 1 gigahertz. So this will be nothing but 1 nanoseconds divided by 6. So it turns out to be 167 picoseconds. Right, so what I had said earlier was around a duty cycle of 18 to 20%, so that is still valid. So the maximum is 20% duty cycle. Here the pulse width is 1 by 6 turns out to be 16% or something like that. So generally we will have a pulse width of around 167 picoseconds for for a clock frequency of 1 gigahertz, especially in a 65 nanometer technology node. Moving ahead, so now let's take a look into the static timing analysis of the pulse latch design. So very similar to how we have done for the flops design. So we had a flop 1 here and flop 2 here in between the combinatorial circuits, and we wanted the output to be captured in the subsequent clock cycles. Right, so here the same thing will be there, just that it is a pulse latch. So a pulse signal is provided to the clock of this particular latch now. It is not a flop anymore, it is a latch design, but it is a pulse latch. So a pulse signal is provided to the clock of this particular latch design. Right, so we have a latch design L1 and L2, and a pulse signal is provided here. So what we really want is the output to be timed. So the output should be captured in the second pulse signal, and then third pulse signal, and fourth pulse signal, and so on. Let's say that the D1 signal has arrived much earlier than that of the pulse signal going high. In fact, it is sufficiently arrived earlier than that of the T setup time, which starts from this going low. Remember that for the latch design. For a latch design, the setup time is coming from the even for a latch design of a positive level of the latch, we will have the T setup time actually coming from the the falling edge, right? Because it can be easily captured during the high level of the clock. But only when it does the transition, it should be made available at least T setup time before the clock level going low. Right, so even for the latch design, pulse latch design, so the T setup time is starting from somewhere here. It's defined from the the negative edge of the pulse signals, right? So, but anyways, the D1 signal has arrived much earlier. So in that sense, the Q1 signal, the output of the latch 1, will be generated the moment the pulse signal goes high. So it is with respect to the propagation or delay of the clock to the Q, right, for the pulse signal, right, for this particular latch design. And then once we have the Q1 output, then it goes to the combinatorial circuit. The output of the combinatorial circuit will be available after the propagation delay of the combinatorial circuit. And then let's say that it arrives much earlier than the T setup time here of this pulse signal for the pulse latch. So remember that the setup time is always with respect to the negative edge of the pulse signals, right, for a positive level of the pulse latch. So if I have this particular timing diagram, so I can easily find out what should be the clock time period. So the clock time period will be nothing but this particular component plus this particular component. The clock time period should be at least, should be greater than or equal to this particular component, this particular component, this particular component minus this particular component, which is the pulse width, right? Here the thing is, we have used TPW to be smaller than the T setup time. Right, so this TPW, the pulse width duration of whatever 167 picoseconds, and T setup time is much higher than that. So in that case, I will have this particular expression valid. Now, what if I have let's say that TPW is 167 picoseconds and the T setup time is 300 picoseconds, then this particular expression is valid. What if I have the TPW instead of 167 picoseconds, I have 467 picoseconds? Right, it is actually touching to the very close to that of the clock level being high used for the latch design, right? So 467 picoseconds and I have the T setup time as 300 picoseconds. Then what happens? So in that sense, we will have the same circuit diagram, the same block diagrams, where the latch combinatorial circuit is there and latch 1 and latch 2 are driven by these pulse signals. And instead of a small pulse here, I will have a larger pulse width, right? And because I have a larger pulse width, now the D signal can actually arrive, in fact, even in the earlier case, the D signal can actually arrive during that particular pulse width. But let's say that because of the larger room here, the D1 signal arrives, somewhere in between the clock level high of the pulse signal. So the Q1 output, which is nothing but the output of the latch 1, will be formed after the T propagation delay of D to Q. Right, so this is D to Q, and in our earlier designs, let me just point it out, it is a propagation clock to Q, because the D has arrived earlier. So this clock will go high only when this output of the latch design will go high only when the clock goes high here. Right, so because D1 has arrived earlier, so the Q1 output will depend on whenever the clock goes high. So the later signal, whichever is the later signal, whether D signal or a clock signal, right? In this case, the clock signal is the latter signal. So we will have the Q1 going high the moment the clock goes high. So similarly, in this particular case, between the clock and the D signals, because the D is arriving late, I will get a Q1 signal with respect to the D signal. Right? So now I have the propagation D to Q here going high. And so that will be my output of the latch 1, and then the output of the combinatorial circuit here, which is the D2 signal, and it will arrive after the propagation delay of the combinatorial circuit, and then it should be ensured that it is available just before the T setup time, right? So again, there's a lot of room here to be captured here, so it can arrive very close to the T setup time, and then get captured into the latch 2 signal, and then we'll get a comfortable output at the output of the latch 2 signal. But if I look into this particular the timing analysis, it is very clear that because the level here is, or the pulse width is very high here than that of the setup time, I can have my clock design such that it is nothing but this component plus this component, and I can design my clock in these two particular levels. So this is my TC value. So the TC value should be greater than or equal to TPDQ plus TPD. Very similar to that of the transparent phase latch clock designs. right? So, but this particular configuration or this particular the TC design is valid only if the T setup time is less than that of the pulse width, or the pulse width is actually very high than that of the T setup time, right? So in a pulse latch, we have two such expressions. One is the expression for when the T setup time, when the TPW is actually low, and one other one is when the TPW is high. Right, when the TPW is low with respect to the T setup time, it is nothing but the propagation clock to queue. It works like the flip-flop design. So it is like the TPCQ plus TPD plus T setup minus TPW. Right. If it works, if the TW is larger, then it works like a latch design, and we have the TC can be designed as TPDQ plus TPD. Right. So we have to look into this particular expressions, this and then the. Whether conditions rather than the expression. If the TPW is sufficiently high, then actually we can use this particular expression. If the TPW is low, then we'll have to use this particular expression to design the clock signal, right? Or in this case, the pulse, the pulse signal or the pulse signal time period, right? So the clock time period as well as the pulse signal time period are the same for the pulse latch. Right, moving ahead. So let's take an example here, a very kind of a very chip level example. So we have the pulse latch here, again given to the similar 4 combinatorial circuits of adder, muxus, and then fed back into the pulse latch here. The pulse width is 150 picoseconds. That has been characterized. That's the pulse width. The signal has been provided to the pulse latch. And the pulse latch is characterized with this setup time, hold time, TPCQ, TPDQ, and TCCQ. Right? So TPCQ of 82 picoseconds and TPDQ of 92 picoseconds is given. We will have a deeper look into this later. And T setup time is 40 and T hold time is 5 picoseconds. The propagation delay of this particular 4 combinatorial circuits are given as 590, 60, 80, 70 picoseconds. And the contamination delay is given as 100, 35, 55, and 45 picoseconds, right? And we have looked into the maximum delay constraint. So we will try to design, apply the maximum delay constraint. So in these last two slides, right, what we had seen is the maximum delay constraint. So this is, it gives us the expression for the TPD in both the expressions, in both the configurations, whether the TPW is low or high. So TPD will always configure or will help in determining the maximum delay constraints. Right. So moving ahead. So for this particular expressions, can we identify what is the clock time period or the pulse time period, the minimum clock time period or the minimum pulse time period, so as to have no setup time failures in this case. So for that particular purpose, we'll have to identify what configuration or what expression we have to use, because in the pulse latch we have 2 different expressions. So based on the TPW and T setup time, we can be able to choose one of the expressions. If the TPW is actually very higher than T setup, then we'll go with that of the closer to the latch expression. And if it is smaller, then we will go with the closer to the flop expression. Turns out that the TPW is actually higher than the T setup time, so we will use the latch expression, which is very simple. So TPDQ plus TPD. So TPD for this 4 combinatorial circuits will be nothing but 590 plus 60, 650 plus 80 plus 70. So it turns out to be 800 picoseconds. And TPDQ here, TPDQ of the pulse latch is 92 picoseconds. So now we'll have the 92 here. So the clock time period is actually greater than or equal to 892 picoseconds. So the minimum clock time period should be at least be 892 picoseconds without any setup time problems.